Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we've got another really great hangout planned for you. We're going to be talking about hypergiants, hypernovae, and Hubble. Oh my! And so, this is a topic that I think many of you are very interested in. So I hope you will get a lot of interaction here. Before I get started, though, I want to remind everybody that there is a video contest going on right now at the European Space Agency's website, spacatelescope.org. I've got a link to it down in the description box. If you love Hubble and you know it, you should make a video, and you have a chance to then. They're going to be having two categories. If you're 25 and under, you're known as the Hubble generation, and so you get a special category. And if you're over 25 like me, you're not special. So, but nonetheless important.
Barely over 25.
And so, there will be two winners, and the winner will get a piece of the Hubble Space Telescope solar panel that flew back in the 90s. So this is a really cool prize. I hope that you will enter early and enter often. They are very excited to look at your submissions. So please, submit your videos. I believe the submissions will stop sometime around March 12th. So time is running out. Also, as I mentioned earlier, this is a topic many of you find quite interesting, so we hope you'll interact with us. You can do that in several ways. You can use the Q&A app. That's my favorite. That's the one I'm looking at right now, and I already see a lot of comments coming through now. Thank you, guys. As well as you can comment on the G+ page, the event page where we're broadcasting from, the YouTube watch page where this is being broadcast. And finally, if you're a tweeter, use the hashtag Hubble Hangout, and we will see that as well, and maybe read it out if we have time, and if there are some interesting ones out there. So we hope that you will interact with us in the following ways, and those ways that I just mentioned, not the following ways. With me, as always, this week is she always is Dr. Carol Christian. She's the HST outreach scientist. Hi, Carol. And hi. Scott Lewis, who's driving the internet and making this hangout hum right along. So welcome, guys.
No pressure.
Yeah. Yeah. Make everything work, Scott.
Make everything work. All right.
So hypergiants and hypernovae are one of the more requested topics I've seen. Questions people ask, and so I know there's a lot of interest there. So I'm really happy to have Dr. Doug Leonard. He's an associate professor of astronomy at San Diego State University. One of his areas of research is he studies progenitors of supernovae. These are the stars that actually explode. So welcome, Doug. It's good to have you on board.
Thanks very much, Tony.
Okay. I like his other specialization, though, too.
Yeah.
Explosion geometry. That is such a hardcore thing. Like, what do you do? Oh, I just study explosion geometry. No big deal.
It's kind of an amazing thing. We don't know the shape of supernovae.
That's right. And in
so
fact, there's
like
a lot.
Forensic astronomy, right? You have to look at the spatter and see what you can infer.
Well, we wish we could. We wish we could actually resolve the spatter.
Yeah.
So you're not like Dexter in space.
No. We have to tease it out of a point source. Try to figure out what the shape is.
Gotcha.
So Doug wrote a paper in Nature, I think it was back in 2009, that was sort of confirming that that a certain class of stars had actually been the progenitor, or the star that actually exploded in a supernova in 2005. And we'll get to that research in just a minute. But before I do, I want to take a step back in just a second, Doug, and talk about the bigger picture here. These hypergiants are part of a category of stars that astronomers have sort of been using for a while now. Now, if you don't know, for those of you who aren't aware, astronomers like to classify things, and stars are the main thing they like to classify, and they do it according to size and temperature and luminosity, all of these characteristics, and they arrange them in a diagram, which we'll get to in a minute. But so let's talk about that. Let's talk about that first, Doug. The classification of stars. How do astronomers do that?
Well, astronomers classify stars really based on two properties that stars have. The first is their color, which indicates what their temperature is, blue being hottest, red being the coolest stars, and they classify them based on how luminous they are. You know, the faintest stars versus the most luminous stars. And they kind of plot all stars on this diagram that shows you the temperature versus the luminosity, and that breaks them up fairly nicely. This diagram was first done about 100 years ago, and we still basically use the same idea today. And it breaks stars up fairly nicely in ways that you can then talk about how stars are born, how they live, where they go on the diagram, and then ultimately my main interest is how they die.
Yeah, so Scott's got a quick diagram up on his page. Can you describe a little bit about what this is, sort of outlining some of the things you just talked about, but can you make comment on this diagram for us?
Sure. Let me pull that up. Yeah, there it is. Okay. I'm having trouble bringing that exact thing up in my window.
Oh.
But
I'm the one with all the pretty colors.
there, I got it now. So, yeah, so what you're looking at there is on the horizontal or x-axis, you see surface temperature. And again, the red is going to be the coolest, and the blues are going to be the hottest. And on the y-axis, it's showing us the luminosity compared to the sun. And what you see is that there are some stars that are extremely faint compared to the sun, those white dwarfs down there. And then there are some that are 10 to the 6th times the luminosity of the sun. That's 1,000,000 times the light output that our sun has. And Tony was mentioning hypergiants. This is a category that isn't shown really on this plot, but if you can imagine extending the plot a little more vertically, above 10 to the 6th, those are the hypergiant stars. So even brighter than what are called supergiants. You kind of run out of adjectives. For a while they were called supergiants, and then someone decided hyper was better than super.
So ultra uber giants?
Yeah, so I was going to go ultra uber super.
If we were naming them today, it would be uber giant. But you know, several decades ago, it was hypergiant. So they're a very rare class of star. Only nature's most massive stars, most initially massive stars, ever enter a phase where they're that bright, that luminous, the hypergiant phase.
Okay, we'll return to that in just a second, but before we leave this topic, Scott has a really nice animation that he was showing earlier that maybe you could step us through also. And this is
I just want to make a comment here. It always amazes me looking back at these diagrams. It's like astronomers are so funny. It's like you have this diagonal line, and so what do we call it? The main sequence. It could be called the diagonal line, but we call it the main sequence. So it's not like really like astrophysics or really conceptual. It's like the main sequence. And what are these other stars? Well, they're bigger than the sun, so they must be giants. Anyway, so it's not very hard to understand.
Astronomers are very historical creatures, and once we get a name,
we're not giving it up.
No matter how bad it is, we stick with it. So these are actually not bad. There are worse names in astronomy.
Oh yeah. Point well taken.
I think that's a great topic for another episode.
Yeah.
The bad names of astronomy.
Bad names, but.
Okay, so Scott's got the animation up. Maybe you could step us through it as he plays it?
Sure. Let's see if I can.
So we're looking at a cluster in Omega Centauri.
Yeah, so this is a sort of an ancient star cluster where you're just seeing thousands and thousands of stars. And the thing to notice is just all the beautiful colors. There are blues, there are reds. And normal people look at this and say, wow, what beautiful colors. Astronomers look at it and say, wow, what beautiful temperatures. And it's now separating those left and right, where the hottest, bluest ones are on the left, and the coolest, reddest ones are on the right. And then the next thing it's going to do is separate these by luminosity. And you'll see the brightest stars do tend to be those blue ones. Usually bluer means brighter and hotter. And the cooler ones are the red ones. And that big strip that Carol referred to as the diagonal strip, I think, that's what's called...
Yeah, the diagonal line.
The diagonal line is what astronomers call the main sequence, and it's, I guess, got that name because that's where most of the stars are. And those are stars that are in the sort of prime of their lives. They're fusing the simplest element, hydrogen, into helium in their cores, which they, in terms of how long stars live, about 90% of their life is spent on that strip, the main sequence. The stars that you see off of the main sequence are in very fleeting moments of their evolution. They spend less than 10% of their time up there as red giant stars. Those are very bright red stars. And then those blue ones there are called horizontal branch stars. And what you're looking at are stars that are on their way to the graveyard for these so-called low-mass stars. All the stars here are less than 8 times the mass of the Sun, and they're headed down to becoming a very compact, bizarre object known as a white dwarf. That's the final graveyard for every star that you see on this diagram here. And I stress this is sort of Omega Centauri is an old cluster of stars, and stars live lives that have a length determined by how massive they are when they're born. So the most massive ones have already died and are no longer in that visible in that cluster. You're looking at just the lower mass stars that are still left that live for billions of years.
Good. Okay, so that sort of explains the way in which astronomers like to organize the stars that they look at up in the sky. But let's get in to these hypergiants in particular. Tell us something. You said they're not very common compared to most stars. They're relatively rare, correct?
That's right. So the stars kind of, if astronomers categorize stars in the ways we just looked at, they also categorize them into 2 big groups, and I kind of referred to it obliquely while I was doing the video. Low mass stars are ones that are born with less than 8 times the amount of mass our Sun has. Stars are born in a range of masses. The lightest ones are about 1/10 the mass of our Sun, and then there's a cutoff at about 8 times the mass of our Sun. All of those stars live lives and then die as a object called a white dwarf. Above 8 times the mass of the Sun, very rare stars. For every 400 stars that nature mints, we think about 1 will be a high mass star.
Wow.
So very rare stars.
Greater than 8 solar masses.
Greater than 8 solar masses. And we don't really know the upper limit. Traditionally, we say it's about 100 solar masses, but there's some evidence that there may be 200 solar mass stars, or perhaps even more than that, especially earlier in the universe. But they're very rare stars. And the most massive of the high mass stars, so probably stars more than about 40 times the mass of the Sun, so these are very rare stars, become these hypergiants during a very sort of quick phase of their evolution. And by quick, astronomy, a million years. But it's sort of a fleeting phase of their evolution.
So let's talk about evolution for a second here. They're born, they have a certain kind of mass, and then they're always hypergiants, right? I mean, they don't turn into a hypergiant from something else, correct? I mean,
No, the theory is that they're born on the main sequence, so they're born as a main sequence star, but then they undergo a phase of their evolution where they become even more luminous than they were as a main sequence star, and often highly variable. They kind of throw off a lot of their material into interstellar space, and sometimes violently through a process we don't completely understand. And these stars are actually expected to throw off so much material that they end up as stars that are sort of denuded of their hydrogen and helium envelopes. And so they end up as these small sort of core of a once very massive star, a type of star known as a Wolf-Rayet star. And that's where they're expected to actually die.
Wow, that's really interesting. So they start in the main sequence for a time, and they live there however long they stay, and then
short amount of time.
Relatively short amount of time. So what is the life cycle of these stars roughly?
So
the lifespan.
Yeah. So if you take our Sun as a base, that's 1 times the mass of our Sun. That's how much mass our Sun has. That's a trick question for sometimes people.
Yeah, I don't know. It's a running joke with us,
It's a running joke with us. Do you know the mass of the Sun?
Yeah, mass of the Sun.
Solar mass.
Yeah, there you go. Our Sun has already lived about 4.5 billion years, and we think it's going to live, and by live we mean it has nuclear fusion powering it, for about another 4 or 5 billion years. When we talk about high mass stars, the lowest mass high mass star, about an 8 solar mass, lives only 40 million years. So 10 billion versus 40 million. Wow. And as you go higher mass, it just gets less and less and less. And so the most massive stars have lives of just a few million years in total. It's kind of counterintuitive, because they're born.
So one of these stars
fuel,
could be
but they
born.
die quicker.
One of these stars could be born, live their lives, and die in the span of less than the time since the dinosaurs were gone here on Earth. So that's amazing to think about. So they don't last long at all, and
they don't last long. And the exciting thing is that they die spectacularly. So that's what interests me most about these high-mass stars. Yeah, well, we all do. Would you just want to shrivel up and become a little nub known as a white dwarf?
I don't know if I'd want to explode though. I mean, that doesn't.
I want you. I'm gonna leave my mark.
Yeah. Talk about spatter. Okay, never mind.
Okay. Yeah. Okay then.
So these are very luminous, very bright stars. They're also very rare. You said less than 1 in 400 become like this?
Well, less than 1 in 400 are high-mass stars. The high mass stars, more than 40 times the mass of the sun, is even less than that. And I don't know what the number is, but it's much less than 1 in 400. I know in the Milky Way galaxy, in our Milky Way, we've only identified it, like, you can count it on a few hands, a couple dozen of these kinds of stars. They're that rare.
So let's move on toward the end of their lives then. These things, as you said, die very spectacularly. And in your Nature paper, you opened up with the line of, we don't fully understand these final stages before a star explodes.
That's a nice sentence. It covers a world of ignorance.
Yeah, I believe you said, our understanding of the evolution of massive stars before their final explosions as supernova is incomplete.
That's a good way of putting we don't know.
So eloquent.
Well, it is a paper in Nature. I mean, you gotta think about it.
And
oh, did he just cut out, or
we lost?
Okay, it wasn't me. Good. Okay, so you're, and this is one thing that you're very interested in. You're very interested in studying this stage of the stars. Now, I want to talk about, we talked about this before we started, about the term hypernova. Sometimes but you're saying that term isn't really used much in astronomy anymore. Why don't you talk about that a little bit?
Well, hypernova is one of those phrases. Remember we said astronomers are historical creatures, and usually the first way someone defines something is how we stick to it. Hypernova is one of these things, though, that it's a morphing meaning as time goes on. In its most general, hypernova we think of as being a very energetic stellar explosion. So we've hinted that these massive stars may explode at the end of their lives. When they explode, they have different luminosities, they have different kinetic energies that they give the material that they throw out into space. And hypernova is, in its broadest sense, supposed to mean a very energetic or luminous supernova. But then you get into the weeds, and everyone means different things about it. So we usually just avoid it and talk about a specific object.
Okay, so if one of these super luminous stars that you're calling it explodes, hypernova may not be the best term to use.
That's right.
Still supernova is just as...
Supernova is what it is. Hypernova tries to give a sense that it was unusual in terms of either its kinetic energy and or its luminosity. And it depends what astronomer you're talking to know which one of those things they mean.
Okay, but I want to clarify something you said earlier, and that was you said that as it's going through the main sequence part of its life cycle, it's expected to lose so much material in the course of its life that none of its hydrogen or helium will be left by the time it's done. What's left behind, and is that big enough to explode?
Yeah, so here's this is what was interesting about the paper. And I should say the paper was done with my colleague Avishai Galyam, who's at the Weizmann Institute. So I'm speaking on behalf of both of us when I talk about this paper.
Right, and he sadly could not join us.
Yeah, it's too bad. It's too bad he couldn't be here. So I hope I don't get anything wrong, Avishai.
And I should mention also, ordinarily we like to give links to these papers, but because this is a Nature paper, I don't think we can. So you'll have to get the issue of Nature.
Okay, fair enough.
Is there a preprint on Archive?
There is. Yeah, if you go on AstroPH.
Oh, okay. Maybe we'll try to find that.
I'll go find that link and I'll tweet it out there. So that's where us nerds hang out for preprints of these papers.
Yes, thank you, Scott. Okay, I'm sorry I interrupted you.
Here's the interesting thing about this. It's expected that these stars die after they've lost all that material. So, Tony, you were asking, is there enough left in the core to create a supernova? And the answer is yes. There's more than enough mass left in just the core to have what's called a core collapse supernova, where the core implodes and then somehow explodes as a supernova. But we actually, from classical stellar evolution theory, we expect that these stars will explode at that stage of their lives. That is, after they've lost the hydrogen and helium. We see supernovae that show no evidence for hydrogen or helium in their spectra, and it has long been assumed that they come from these once very massive stars, just the cores now exploding. One of the interesting things in the game I play, which is a star explodes, and you then trawl through the Hubble Space Telescope archives looking to see if anyone happened to take a picture of that star before it exploded. And more and more frequently, the answer is yes. And
25 years is a long time.
It's a long time. And you just hope someone took a picture of the galaxy this thing was in for some other reason, usually. And you want Hubble because you need the really fine resolution in order to distinguish the star that may have exploded as a supernova from nearby stars. So you really need the resolution of Hubble. And the interesting thing is we see these called stripped envelope supernovae all the time, no hydrogen or helium. We expected that when we did progenitor studies on them, we would find, sitting there, one of these Wolf-Rayet stars that had lost its hydrogen and helium envelope. To date, we've discovered none. So that's one of the mysteries in this line of research. And the study that I did in 2009 was a supernova that showed hydrogen in its spectrum, but the surprise there was the luminosity of the star that we saw in the pre-explosion image, and we can show a graphic where you can see all this.
Actually, I actually want to come back to this. I know that we
come back to
talk about that particular observation in just a second, but before, I just want to take a step back for just a minute, and let's talk about supernovae in general.
Yeah,
okay?
We haven't really done that.
So let's do that first, and then we'll go to your paper. In the slides that you sent us, there was one of there's basically two classical types of supernovae.
That's right.
And I wonder, Scott, if you might be able to put that up for us.
Yeah, I think it's the third slide.
Yeah. So, and I want to kind of give people a background on these different. So there's more than one type of manner in which a star may explode, right?
That's right. So this slide shows what I call the two classical types of ways stars explode. There's a lot of interesting research being done right now. There it is. Okay. A lot of interesting research being done right now on other mechanisms that might lead to a stellar explosion. But these are the two kind of traditional ways that we know stars can die. And what you see, are we looking at the graphic?
Yeah.
Yes.
So it's up. He's got it up now.
Okay. So when I said that stars born with less than 8 times the mass of the sun don't explode at the ends of their lives, they just become white dwarfs, that's the way most of them die. But occasionally, one of them, and it's a pretty rare one, maybe 1 in 200 or 400 or so, of these white dwarfs, will be fed by a companion star, like maybe it was in a binary system, and the other star will start dumping material onto the white dwarf. And we won't talk much about this kind of supernova, but basically a white dwarf is a bomb waiting to happen. It's carbon, it's oxygen, and if you can just get the density of the thing up high enough, then that carbon and oxygen can fuse and release a tremendous amount of energy all at once and rip the whole star apart in what's called a Type 1a supernova. It's
right, and we've talked about those before, where they're known brightnesses and they're good yardsticks for measuring distance and things like that. So so that's a more common way, right?
In nature, there's about equal numbers of Type 1a and the other kind, which is the core collapse. Type 1a have been very popular lately because, like you said, they're very good distance indicators, and so we can use them to get distances. and they're very luminous, and so we can get distances to very far away in the universe.
Yeah, so Carol Scott and I have done many, at least one, probably I think several on Type 1As. So I think you guys can definitely do reference to those on our Hangout playlist. So let's talk about the other type, though. These are for the big stars, the greater than 8 solar masses one. What happens there?
Yep, greater than 8 times the mass of the sun. What happens there is the core of these stars is massive enough to have enough gravity to squeeze the core hard enough to make it dense enough so that elements will continue fusing all the way up to very heavy elements, all the way up to iron. So past carbon and oxygen on the periodic table, all the way up to iron. But the problem with iron is it's like you can't get blood out of a stone. You can't get any more energy out of iron.
That's right.
It's just the laws of quantum physics. You can't fuse something heavier, iron into something heavier, and extract energy.
Yes,
and so
I always thought that was amazing.
Yeah, so once the iron core is built up, it's ready to die very soon, actually, after the iron core develops. And what basically happens is the core at that point is extremely hot, but no more fusion can happen. And it's basically being supported by thermal pressure because it's really hot, but also a weird quantum mechanical pressure known as electron degeneracy pressure. Electrons don't like to be squeezed too close together, basically. But what happens is the electrons they get squeezed so hard that they actually join with protons to form neutrons. And the electron degeneracy pressure disappears in sort of a runaway, and the whole core implodes all at once. And it goes from something that's about the size of the Earth, maybe down to the size of a small city in less than a second. It's, astronomers are usually patient people. This thing happens in 1 second. The core implodes. And borrowing the line from the Nature paper again, we don't quite know how she does it, but nature turns that implosion into an explosion. Basically, it forms what's called a neutron star in the center, and then in the classical theory, the envelope smashes into the neutron star, and a shock wave develops that then expels the envelope out into interstellar space, and you have what's called a core collapse, or usually we call it a Type 2 supernova.
Type 2 supernova, and what's left behind typically, you said, is a neutron star?
Neutron star or a black hole.
Good. Okay. So how do we get there? What is just a little, really big star, much bigger?
We want to make black holes.
Yeah. So we're pretty convinced nature does make black holes, and we're pretty convinced that she does it through this core collapse process of very massive stars. Exactly which stars lead to black holes and which stars lead to neutron stars is a matter of pretty fierce debate. The canonical theory is that the most massive ones lead to black holes. So maybe more than 25 or 30 times the mass of the sun might just go and leave a black hole. And then the lower mass leave neutron stars, though we don't really have good observational constraints on that theory. There's also some belief in the community that some stars might just snarf directly to a black hole with no fireworks, no supernova. And so one thing that's never been seen, but also has not been looked for very much, is disappearing stars.
That's an interesting idea. No explosion at all, huh?
Yeah.
Just blink.
Yep. Could a star just be there today and then blink out tomorrow with very little observational signature?
Wow. That would be hard to find, I would think, in Hubble data.
Well, people don't look for it. People look for changes in the other direction. Something becomes very bright that was very faint. And people are just now starting to look for the reverse. Look to see if they're actually disappearing stars. So far, they're no good candidates.
That's very interesting. I've never even considered that. That's amazing to think about. Wow. Yeah. Okay. So let's get back to your observation of this one supernova. It's called Supernova 2005 GL. That sounds like a model of a car. You said that you weren't sure. There was some evidence suggesting that maybe this was a hypernova that had exploded, but there wasn't much sure. So you said what they do is you go back and you look through the Hubble archives and you try to find an observation that maybe looks at the star or has seen the star in the past, so you can get some information about its characteristics. Is that pretty accurate about what happened here?
Yeah. So I don't know if Scott still has the pages up, but slide 8 shows what Tony was just talking about.
Okay, as he's pulling that up.
Yeah.
Yeah, here we go. Okay.
So, yeah, so this was a star, a supernova, in 2005. And if you're looking at that slide, in the upper left, you just see a ground-based image of the supernova. It was in a galaxy only 220 million light years away. So that's in our backyard.
Only 220 million light
only
years.
220. It's not the closest galaxy, but it's pretty close to us. And the picture in the upper left there, the little arrow or the line, the hash line, shows the supernova occurring in the spiral arm of that galaxy.
There it goes.
Wow,
NGC,
cool.
NGC 266. So that, bear in mind again, that's one star, and you can kind of compare that luminosity to the entire galaxy it's in, which is, 100 billion stars. So for a while, it rivals the whole galaxy. And all those other stars you're seeing in the picture, those are Milky Way stars. So they're really close to us. Yeah, so consider, maybe 100 light years versus 210 million light years, and they're the same apparent brightness. It gives you a sense of how luminous these things are. So, yeah.
So across the bottom there are some observations in different time periods.
Yep. So this was 2005. And if you actually look at those the bottom strip, you see the thing that says during, and it says 2005. That's an image of the supernova. So this is an extreme close-up. We're talking like a square arc second and a half or so of the sky. Very small patch of this galaxy. And that is just a picture of close-up of the supernova. Okay? And it was actually taken using an infrared telescope on the ground, where we could use adaptive optics and get really good resolution from the ground in the infrared.
Okay.
And then the trick here is, a good thing is that 8 years before, an astronomer using Hubble had photographed this galaxy for a completely different reason, but in that photograph was this exact region. And if you look at the 1997 on the left there picture, you see that white circle indicates where today we see the supernova. Now, this is a picture only an astronomer could love, but when we saw that, we fell out of our chairs because those little pixels there are very bright. Black means bright, and this thing's 210 million light years away.
Yeah, there's about 4 of them.
Yeah, and that's really, really bright. And when we did the calculation, that amount of light coming from something, so that's what we call the putative progenitor star. Maybe that's the star that blew up as the supernova in 2005. You don't know that. You just, right now, you have what's called a spatial coincidence. There is a star there, it has some bright pixels, and it's now a supernova there. Could be a foreground star totally unrelated to the supernova, for all you know. But if that is the progenitor, it's extremely luminous, and when you do the calculations, that amount of light is over 1 million times the luminosity of our sun.
So that's consistent with these being one of these hypergiants.
That's right. But so Avishai and myself and a bunch of colleagues wrote a paper saying, well, we have this spatial coincidence. If this is one star making all that light, then it's an extremely luminous star. And the only stars we know that get that bright are these hypergiants. And conventional theory says they shouldn't explode. They should have another 500,000 to 1 million years to do their shedding of all their mass and then explode as one of these Wolf-Rayet stars. So it was a controversial finding and suggestion that a hypergiant exploded. And so what you do is, if you have a controversial finding, you want to prove that it actually is true. And that's where we had to wait for 2 years, because you have to wait for the supernova to go away. You have to wait till all the fireworks of the explosion disappear so that you can get that crucial picture on the third frame there that says 2007. That's another Hubble Space Telescope image taken after the supernova had faded beyond detection. And you want that picture to show that that star in 1997 isn't still sitting there. Because if it's still there, then that star didn't blow up. But what you see is in the white circle, the light is gone that was there in 1997. Whereas the other stars in the frame, indicated by the red circle and the green circle, red circles and green circle, they're still sitting there, but that one star has disappeared. And so that is what turned an astrophysical journal paper into a Nature paper, is that one picture taken by Hubble.
That's amazing.
Because we proved it, yeah.
Here you have 3 frames in a movie that spans 10 years, and I mean, it's just, I keep thinking back to my early days being taught about astronomy, and everybody thought that the universe was a very static place, and nothing ever changed or nothing ever happened, and this is just, I can't see stuff like this without being totally humbled. It's just awesome.
Aristotle would not have believed this.
Yes.
and Plato would not have believed this.
Yeah.
Because there was something in the heavens that is definitely changing. But they also wouldn't have seen this.
That's true. Very true. Very true. Well, this is outstanding. So, what have you seen this anywhere else? Are there any other observations like this, or is this the only one that kind of supports the idea of these superluminous stars exploding a little bit prematurely?
There have been. Since that time, there have been other events similar to this with even better pre-explosion pictures. In this case, all we had was this one image in one filter, so we don't even know what color the star was. All we know is its luminosity. And we kind of had to paste together clues from the supernova itself to convince us it was one of these hypergiant stars that had exploded, to really make a convincing case for it. This remains a very controversial finding. And
so you'd like to see more of these, I guess.
Yeah, you would like to see more of these. And there have been, but they're also controversial. So there's another famous one. It's if you want the phone number, it's Supernova 2009 IP. But it was another one of these stars, but it had even better pre-explosion imaging. It had lots of pictures taken, and you can actually trace the variability of the star prior to it exploding. It was very sort of eruptive, and it would increase in luminosity and then decrease in luminosity, and it was very restless. And then one day, it apparently exploded for good and became a bona fide supernova. So like I said, these stars are in a very unstable part of their lives as hypergiants, where they're just throwing off a lot of material into interstellar space. And then the controversy is whether the final thing really was an explosion, the final thing in this this other supernova, or not. And there's a disagreement in the community about that. So I wouldn't say that this study we did was at all the final word. It was kind of the first word on whether these hypergiant stars explode as supernovae, and also what stars actually become hypergiants has now been thrown into question.
Really? In what way?
Yeah. Well, there are some theories out there now that maybe you get one of these stars not by being born as an enormously massive star, but maybe a star that's born in a binary star system can gain mass from its companion during its life, and create one of these things, one of these hypergiants, through a different mechanism, through sharing material from a companion. And that might explain some of the oddities, like watching this thing explode when it did, and other characteristics of these hypergiant stars that don't seem to quite fit with that nice model of a single, very massive star going through a brief phase of its evolution.
Well, it doesn't have to be mutually exclusive, though. It doesn't have to be either or, does it? I mean, you could have both things going on: a star being born that big, and also mergers going on.
Sure, you sure could, and it might also get you out of the pickle of having to have one of these stars exploding during a phase of classical evolution theory where they're not supposed to.
Right. Yeah.
This discovery, in my mind, if it was one of these single, very, very massive stars, to me, the biggest thing, the thing that excited me most, was that we showed a star more than 50 times the mass of the sun actually exploded.
Yes.
Because there was a lot of theory out there saying these stars should just go directly to black holes, a direct collapse. Should be one of these disappearing stars, not a supernova. So that was interesting. But then the second thing is they're exploding in a phase where they're not supposed to. So that was also intriguing.
Well, let's go. Okay, I want to move on. We're running out of time, and I want to get to some questions and comments. But let's talk a little bit about Supernova 2007 FO.
Oh, yeah.
And NGC 7714. I wonder if, Scott, if you wouldn't mind putting up that slide for us. This was an observation where I believe you thought this was one of those examples. You want to discuss it a little bit?
Yeah, so that graphic is up now?
Yeah, Scott's got it up.
Let me see. So assuming it's showing a picture of the galaxy. I'm seeing a picture of Scott.
Yeah, unfortunately. Yeah,
my screen share is not loving me today.
Yeah,
it's a beautiful image taken of NGC 7714. And are we seeing that yet?
Hang on, I'm not going to be able to.
He might have some problems with it. His browser keeps crashing whenever he tries to do the screen share. So.
Well, I can describe it. This is a galaxy. It's a rare galaxy in the local universe. By local, this is about, I think, 100 million light years away, even closer. But it's rare in that it's actively interacting with another galaxy. And so it's got a very, very interesting shape to it. A picture's worth 1,000 words here if it's up.
Yeah, let me give it a try. He's having difficulty. Let me see if I can pull it up. I've got it up right here. I just it's not going to be nice. Okay.
There we go. Is that it?
Yeah.
All right. Click on mine, Elena. Okay. So there's what you're talking about.
Yes. So that beautiful galaxy, that picture on the right that you're seeing there, that was Hubble's image that was taken. And again, this is work Avishai and I and Derek Fox also were involved with. And we are again interested in a star that exploded there, supernova 2007 FO, which you see in the left-hand image there, ground-based image. That arrow points to a supernova. And then the right-hand image is the Hubble image. And this was one of those supernovae that had been stripped of its envelope. So it didn't show hydrogen in its spectrum.
This was the way it was supposed to go, right? This was the...
Yeah, and we were hoping beyond hope that we would be able to nail a Wolf-Rayet progenitor star for the first time for one of these stars. And what was exceptionally exciting about this was Hubble Space Telescope had not only imaged this, but it had imaged it at ultraviolet filters. And so these stars are extremely hot and extremely bright in the UV. And so we got Hubble to look at it again, and that's what created the image that you see. But it's a beautiful image. All we cared about was the 1 arcsecond field around.
Right. Those few pixels around there.
So it's kind of funny. I'd stared at that 1 arcsecond square, for a long time. But then when the Space Telescope Science Institute made this nice image, color image, I was like, wow, that's what the whole thing looks like. You focus in, so missing the forest for the trees.
Yeah.
But unfortunately, Sadly, what we did was add to the growing list of no progenitor detection, no star detection in the pre-explosion image. And unfortunately...
Meaning you couldn't find an image prior to this that had the star in it?
No. There's an image, but there's no disappearing light. There's no star that was there in the pre-explosion image that is now gone in the post-explosion image. Those are shown on the bottom of the slide there. The red circle represents our rough uncertainty in the position of the supernova. There's just a before and after picture there, pre and post as they're called. And to the best of our ability to subtract light one from the other, we don't seem to measure any disappearing light, meaning that whatever star was there was beyond the detection limit of the pre-explosion image. And this is what has been true for the dozen or so of these types of supernovae that have pre-explosion images. All we have are holy upper limits, Batman. It's you try to get excited about upper limits. It's not as exciting as when you actually see the star, but it adds to the list of upper limits.
Okay. Well, so that one turned out not to be what you had...
I did want to say for people to go and look actually at the 7714 image, because it is actually very spectacular.
Do you want to comment on
galaxies moving through each other and all that? It's an interacting galaxy system, which is...
Interacting galaxies create lots of new stars. The gas gets compressed, and we see lots of supernovae, core collapse supernovae, in interacting galaxies. And so, and especially this kind of supernova, it turns out, in these interacting galaxies. So the Hubble image just shows NGC 7714. There's another image in one of the slides I sent that shows the culprit. You can see the galaxy that plowed through it off to the left of the image that you're seeing there. And those two galaxies are doing a dance. They may merge in the future. They interacted 100 or 200 million years ago.
Okay, so I want to get to some of the questions and comments that we have here before we lose too much time. Let's see. Ben Gaisley is commenting, big stars live fast and die young. Yes, they do. Wout van der Heide, I'm going to have to learn how to pronounce your name because you're here at almost every hangout. Isn't Eta Carina, and we are glad you are, by the way, isn't Eta Carina a candidate for a hypernova? If yes, what could be learned from a hypernova occurring this close?
Yeah. So one of the slides, I have a picture of Eta Carinae. It's the most famous of these hypergiant stars. I don't know if anyone can get that graphic up.
Yep.
But it's the most famous. It's what's called a luminous blue variable, LBV, as they say. And this is a star that we have witnessed up close and personal. That's it. Up close and personal. It's in the Milky Way, and what you're looking at there are the results of an enormous eruption that a very massive star. The mass estimates range from 100 to 200 times the mass of the Sun. In the middle there, in the mid 1800s, it became the brightest star in the sky for a time, when it had this outburst, which we now see as those cones of material racing away.
Here's one lobe, and here's another lobe.
Yep. Yeah. And so this is one of these very restless stars that is, we think, on its way to dying. We do not, to answer the question, we would be surprised if this thing exploded as a supernova tomorrow, because our theory says it should have another 500,000 to 1,000,000 years of doing that kind of stuff, these mini explosions, before it would end up as a Wolf-Rayet star and then die without its hydrogen envelope. So we don't think it should explode, but like I said before, there's a lot of uncertainty here because supernova 2005 GL, supernova 2009 IP, apparently these luminous blue variables can explode, and so our whole theory for this thing is being called into question. And if it were to explode, oh my God, that would be awesome. Because it would be great. It's not a Death Star. We wouldn't be harmed by it. It's not that close. And astronomers would just learn so much about exploding stars if it would just explode.
Yes, but I do want to. He brings up an interesting point in the second part of his question, which was what would happen if one happened very close to us. I mean, there are these kinds of explosions can actually affect the Earth if they happen close enough, correct?
That's right. That's right. Yeah, I'm not a biologist, but the people who are and know, when one of these stars explodes, there's a lot of radiation and stuff that's harmful to humans given off, and if it's close enough, it can damage our atmosphere and move our protective layer. And so someone worked out the sort of the kill radius around the Sun. Something on the order of 100 light years, I've heard, is where you don't want a star to be, to have it blow up. Maybe less than that, 50 light years. There are no stars that are that close that we have to worry about.
One day I want to do a hangout on something called the Great Filter, and it's this idea that there are these things that can happen in the evolution of life on Earth that can actually prevent civilizations from forming, and one of those filters could be a supernova explosion. Another one would be gamma ray bursts if they happen close enough, things like that. So these things are pretty effective if they're close enough. Let me get to another question. Sev Dust Bunny, hello Sev. Are some of the main sequence stars colliding to become super hypergiants, or are they always so massive? And would star formation still be occurring in such an old cluster? He's talking about the Omega cluster we were looking at earlier, as in that video, as would short life stars. So basically, you commented on this earlier. Can some of these main sequence stars collide or merge? And the answer was yes, that can happen. But do you have anything that you want to add to that?
Yeah, the only thing I'd add to that is that I was talking about how maybe some of these luminous blue variables or hypergiants come from stars that may have gained mass through this process that's just been described, this accretion of one star material onto another. And one of the ideas is that you have a binary star system, 2 stars orbiting a center of mass, and the more massive one lives its life and blows up as a supernova, having dumped a whole lot of material in the companion that then gets ejected away and is weird. It's all polluted with all the material of the supernova. It gained a lot of mass, and that could become one of these luminous blue variable kinds of stars. So the person who writes the question is onto something with the idea that stellar collisions, stellar mergers, could lead to these very unusual kinds of stars, these rare kinds of stars.
Awesome. Got a good question here too I want to ask. I want to get your thoughts on this. Would multi-wavelength observations, such as X-ray and radio emissions, help pin down the origin of these supernovae? Do you use these wavelengths in your progenitor studies?
Yes, we do. But for... let me think about that. For the actual progenitor studies that I've been doing, visible wavelength is the primary, but more and more, it all depends on whether we have data in these other wavelengths. And typically we do not, but occasionally we do. And so we do actually, for some of the progenitor studies, have infrared data that adds to our color information of the progenitor. There's been 1 or 2 studies where we have all wavelengths, you know, ultraviolet out through infrared, pre-explosion pictures where we can really nail down what's called the spectral energy distribution of the thing. And then, of course, once a star explodes, if it's really close by, we train our X-ray telescopes on it, our radio telescopes on it, to study the explosion in more detail. But at this point, we're just darn lucky if we have pre-explosion X-ray radio. But people look, yes.
Yeah, you know what, Carol, this is sort of highlighting something. This discussion is kind of embedded in it, is just how important having a telescope up for 25 years is. I think, I mean,
Exactly.
in some ways, I think it makes Doug's work possible, because you can always, for 25 years, or may have, the chances are high that there may be previous observations of something.
And the other thing is that these are, I mean, for the aficionados, these are NGC objects, which is a famous catalog, and so galaxies in the NGC catalog tend to have studies done about them because they're close enough that you can resolve them, see star formation regions and stuff like that. So there are chances that that a galaxy like that might be imaged by Hubble, which is
there
good.
are actually Hubble programs now that are specifically taking pictures of the galaxies just for this reason.
For the reason, yeah.
Surveys.
Okay, I'm on YouTube now. I'm sorry, I want to get through as many of these as I can.
Okay.
So I want to try and keep our answers
Yep,
as short as
I was
possible.
going for that question
If
now.
stars, Torch, this is from Torch Woodduck on YouTube. If stars stop fusing elements at iron, how are heavier elements ever produced? Thanks. My name is Mike from Essex, England. Thank you, Mike, and that is a great question.
That is an outstanding question, because we know that there's gold in the universe and silver,
Yeah.
but we also know that these elements are extremely expensive, which must mean that they're very rare. And it is a great question. How do you produce elements heavier than iron? And the short answer is astronomers, well, we don't know. We don't have any definitive evidence for how nature does it, but one of the ideas is, guess what? A supernova.
Supernova.
Right in the immediate aftermath of a supernova, just as the explosion has happened, there's a very rare condition that exists where you have iron nuclei, iron group elements, nuclei, so 26 protons around, the heaviest that is produced by nuclear fusion, and you have a whole lot of free neutrons around. That doesn't exist very often because neutrons decay very quickly, like 10 minutes they decay into other things. So in the immediate aftermath of a core collapse supernova, you've got this rare condition of iron nuclei and a whole lot of free neutrons. So remember this neutron star that's formed. There's some free neutrons also in the ejecta. And what we think happens is that these neutrons sneak into the iron nuclei because they don't have any charge. They're neutral. So they just bombard these iron nuclei and build these huge isotopes of iron and nickel and things like this. And then these are very unstable isotopes, which the neutrons essentially then change into protons through the miracle of quantum mechanics. And you then have just done alchemy, and you've produced a heavier element, an element with more protons in it. So it's not through fusion. It's through this process called neutron bombardment, which we think takes place in the aftermath of a core collapse supernova. So I hope I explained that well.
Yeah, you did a very good job, and
I tried to keep it tight. But we think a supernova is responsible for the wedding ring on your finger.
I've got a question over here from Twitter. Should I risk screen sharing? No, let's just read it out loud first. This is from Demir Salopak. I hope I pronounced that right. This is, how do white dwarfs die? So we've talked about the ending of the life cycle. So how do we know how white dwarfs die?
Left to their own devices, they just cool off and become colder and colder and darker and become what might fancifully be called a black dwarf because they no longer give off much light. But that takes billions of years. White dwarfs have a known cooling rate with time. So if they're left to their own devices, it's a very unremarkable or sort of not explosive by any means death. They just cool off and become darker and darker and fainter and cooler and cooler. This is the fate we think awaits our sun.
Yep.
The rare one that gets matter dumped onto it, we think can explode as a Type 1a supernova. So I've been talking about how well we know these progenitors of the core collapse. I should point out we have zero observational evidence that our whole scenario for Type 1a supernova is in fact correct.
Yeah.
We've never seen in a progenitor, a pre-explosion image, a white dwarf sitting there getting ready to explode. Part of the problem is they're very faint. And we've actually had very hard time finding any evidence for a companion star dumping material onto a white dwarf prior to the explosion. And so there's a lot of mystery surrounding these Type 1a supernovae as well.
Okay, so Peter Waldman, I'm going to have to let your comment or question be the last one because we're out of time, but I picked it on purpose. Is HST going to take more deep field observations now that VLT with MUSE has proven to be more sensitive in the detection of galaxies in that area? And the reason I picked that question is it is a great segue into what we're going to be talking about next week at our hangout, where we have a Frontier Fields hangout coming up, where we're going to be discussing this very thing, supernovae and Frontier Fields. So we hope you'll tune in next week. I'm going to have to stop there, I guess. We're out of time, but I wanted, Doug, this has been awesome. Thank you for taking time out to talk about research. This has been a really interesting subject. I think we should come back and visit this again. This topic is, if you are, do you have any more papers in the works coming up on this topic?
Hopefully, but as of now, all these papers are kind of these upper limits or bare detections. So the 2005 GL was very exciting. A lot of scientists putting bricks in the wall, not starting a whole new wall.
Okay, so hopefully we'll have you back to talk more about this topic because it's really interesting.
Yeah, it's really great having you.
All right, so thank you guys. This has been great. That's it for this week, folks. As I mentioned before, our topic next week is going to be Frontier Fields and a lens supernova. So we hope you will tune in and watch. We'll have the principal investigators for that. That'll go with the press release that's coming out that same day. So we hope you'll come back. Scott, Carol, awesome hangout as always. Thank you very much, everybody. Thanks for watching, and as always, keep
looking up.
Keep looking up. That's right. Coming through now. Thank you, guys. As well as you can comment on the G+ page, the event page where we're broadcasting from, the YouTube watch page where this is being broadcast. And finally, if you're a tweeter, use the hashtag Hubble Hangout, and we will see that as well, and maybe read it out if it's if we have time and if there are some interesting ones out there. So we hope that you will interact with us in the following ways, and those ways that I just mentioned, not the following ways. With me, as always, this week is, she always is, Dr. Carol Christian. She's the HST outreach scientist. Hi, Carol. And Scott Lewis, who's driving the internet and making this hangout hum right along. So welcome, guys.
No pressure.
Yeah. Yeah. Make everything work, Scott.
Make everything work. All right.
So hypergiants and hypernovae are one of the more requested topics I've seen, questions people ask, and so I know there's a lot of interest there. So I'm really happy to have Dr. Doug Leonard. He's an associate professor of astronomy at San Diego State University. One of his areas of research is he studies progenitors of supernovae. These are the stars that actually explode. So welcome, Doug. It's good to have you on board.
Thanks very much, Tony.
Okay.
I like his other specialization, though, too.
Yeah.
Explosion geometry. That is such a hardcore thing. Like, what do? Oh, I just study explosion geometry. No big deal.
It's kind of an amazing thing. We don't know the shape of supernovae.
Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we've got another really great hangout planned for you. We're going to be talking about hypergiants, hypernovae, and Hubble. Oh my! And so, this is a topic that I think many of you are very interested in. So I hope you will get a lot of interaction here. Before I get started, though, I want to remind everybody that there is a video contest going on right now at the European Space Agency's website, spacatelescope.org. I've got a link to it down in the description box. If you love Hubble and you know it, you should make a video, and you have a chance to. Then they're going to be having two categories. If you're 25 and under, you're known as the Hubble generation, and so you get a special category. And if you're over 25 like me, you're not special. So, but nonetheless important.
Barely over 25.
And so, there will be two winners, and the winner will get a piece of the Hubble Space Telescope solar panel that flew back in the 90s. So this is a really cool prize. I hope that you will enter early and enter often. They are very excited to look at your submissions. So please submit your videos. I believe the submissions will stop sometime around March 12th. So time is running out. Also, as I mentioned earlier, this is a topic many of you find quite interesting, so we hope you'll interact with us, and you can do that in several ways. You can use the Q&A app. That's my favorite. That's the one I'm looking at right now, and I already see a lot of comments. That's right. And in fact, there's a lot.
Forensic astronomy, right? You have to look at the spatter and see what you can infer.
Well, we wish we could. We wish we could actually resolve the spatter.
Yeah.
So you're not like Dexter in space.
No. We have to tease it out of a point source. Try to figure out what the shape is.
Gotcha.
So Doug wrote a paper in Nature, I think it was back in 2009, that was sort of confirming that that a certain class of stars had actually been the progenitor, or the star that actually exploded in a supernova in 2005. And we'll get to that research in just a minute. But before I do, I want to take a step back in just a second, Doug, and talk about the bigger picture here. These hypergiants are part of a category of stars that astronomers have sort of been using for a while now. Now, if you don't know, for those of you who aren't aware, astronomers like to classify things, and stars are the main thing they like to classify, and they do it according to size and temperature and luminosity, all of these characteristics, and they arrange them in a diagram, which we'll get to in a minute. But so let's talk about that. Let's talk about that first, Doug. The classification of stars. How do astronomers do that?
Well, astronomers classify stars really based on two properties that stars have. The first is their color, which indicates what their temperature is, blue being hottest, red being the coolest stars. But if you can imagine extending the plot a little more vertically, above 10 to the 6th, those are the hypergiant stars. So even brighter than what are called supergiants. You kind of run out of adjectives. For a while they were called supergiants, and then someone decided hyper was better than super. So
ultra uber giants?
Yeah. So I was going to go ultra uber super.
If we were naming them today, it would be uber giant. But several decades ago, it was hypergiant. So they're a very rare class of star. Only nature's most massive stars, most initially massive stars, ever enter a phase where they're that bright, that luminous, the hypergiant phase.
Okay, we'll return to that in just a second, but before we leave this topic, Scott has a really nice animation that he was showing earlier that maybe you could step us through also. And this is
I just want to make a comment here. It always amazes me looking back at these diagrams. It's like astronomers are so funny. It's like you have this diagonal line, and so what do we call it? the main sequence. It could be called the diagonal line, but we call it the main sequence. So it's not like really like astrophysics or really conceptual. It's like the main sequence. And what are these other stars? Well, they're bigger than the sun, so they must be giants. Anyway, so it's not very hard to understand.
Astronomers are very historical creatures, and once we get a name,
We're not giving it up.
Yeah.
No matter how bad it is, we stick with it. So these are actually not bad, and they classify them based on how luminous they are. You know, the faintest stars versus the most luminous stars. And they kind of plot all stars on this diagram that shows you the temperature versus the luminosity, and that breaks them up fairly nicely. This diagram was first done about 100 years ago, and we still basically use the same idea today. And it breaks stars up fairly nicely in ways that you can then talk about how stars are born, how they live, where they go on the diagram, and then ultimately my main interest is how they die.
Yeah, so Scott's got a quick diagram up on his page. Can you describe a little bit about what this is sort of outlining some of the things you just talked about, but can you make comment on this diagram for us?
Sure, let me pull that up. Yeah, there it is. Okay. I'm having trouble bringing that exact thing up in my window.
Oh.
But
I'm the one with all the pretty colors.
there, I got it now. So, yeah, so what you're looking at there is on the horizontal or x-axis, you see surface temperature. And again, the red is going to be the coolest, and the blues are going to be the hottest. And on the y-axis, it's showing us the luminosity compared to the sun. And what you see is that there are some stars that are extremely faint compared to the sun, those white dwarfs down there. And then there are some that are 10 to the 6 times the luminosity of the sun. That's 1,000,000 times the light output that our sun has. And Tony was mentioning hypergiants. This is a category that isn't shown really on this plot,